Now let's see how does it work for continuous random variables. But for continuous distributions, actually a number of examples from our real life when we know joint distribution of two statistically dependent continuous random variables is very limited. So let me consider just a purely academical example, just to show you how can we apply these formulas to continuous case. So the example is as follows. We have a set let it be, I don't know, let it be G. And joint PDF of x and y is equal to constant inside G and to 0 outside of it. So joint PDF is constant, so C is just a constant if x, y belongs to G and to 0 otherwise. So, and we are to answer the same questions. So, are x and y statistically dependent or independent, and are x and y correlated or uncorrelated? So let's try to do this. But the first step, actually maybe it's better to say step number 0 here, is to find this unknown constant. So you see that they gave us the PDF, but we don't know this constant. We don't know what this C is. So as in scalar case, in two-dimensional case, to find C, we are to apply one of the properties of the PDF, that integral of the PDF, integral over the whole plane, so from minus infinity both to plus infinity both over x and over y, is to be equal to 1. So integral from minus infinity to plus infinity of our function is to be equal to 1. But so what do we see here? We see that this function that is integrated here is not equal to 0 only inside G. So this is actually integral over G of what? Of this constant. So inside of it, our function is equal to C. So dx dy. Or we can say so that this is C times integral over G dx dy. So what is this? What is this? This is an integral over region G of what? Of 1. And you should know that integral of this kind is always equal to the area of the region. So if function that is integrated is equal to 1, so we can say that there is no function here between integral and dx dy. So if here we see just 1, so this integral is equal to the area of this region. So G is a square, and so each side of this square has length equal to square root of 2. So as this is 1 and this is also 1, so this side is square root of 1 squared plus 1 squared, so square root of 2. And so the area of the whole square is square root of 2 squared, that is 2. So I can say that this is C times area of G, and this area is equal to 2. So this is 2C, and this is equal to 1. So that means that C is 1/2. C is 1/2. So we have found the unknown constant. Now, so how do we check if a pair of continuous random variables are dependent or independent? So we need to check if the whether the joint PDF is equal to the product of marginal PDFs. So we have already got the joint PDF, it is given, and now we are to find marginal PDFs. So, and marginal PDFs can be found integrating joint PDF over X if we need marginal PDF of Y, or over Y if we need marginal PDF of X. So let's try to do this. So marginal PDF of X is equal to an integral from -infinity to +infinity of the joint PDF over Y. So this is probably the most difficult part of this example, of this problem. So what are the limits of integration here? So we are integrating our function over y, so we have dy here, and we see that limits of integration are actually, they depend on x. So if we are somewhere here, for example, if we are here, if x is equal to 0, and we are integrating our function over y, so function is equal to c to 1/2 from -1 to +1. If we are here, if x is equal to 0. But if, for example, we are somewhere here, if x is equal, let's say, to 1/2, so then what? Then I am to integrate it by over y from this point to this point. So limits of integration here depend on x. So let us think a little bit. So when we go along a line parallel to OY axis, where our function, our joint PDF, stops to be 0 and starts to be 1/2. So it does so when we cross this line. So when we cross this line, it switches from 0 to c, to 1/2. And when we cross this line, it switches back from 1/2 to 0. So our limits of integration are actually lower limit is this line and upper limit is this line. So to write down the limits, we need equations of these functions, of these lines. So lower limit is this, so this line. It looks like a modulus, like y equal modulus x, but minus 1. So it would be modulus of x if it were starting from here. So, but now we can say that, so this function is y equal to modulus x minus 1. So, and this is the lower limit of integration. And so this is 1 minus modulus x. So y is equal 1 minus modulus x. And this is the upper limit. So, and everything else is quite easy. Just we can say that this one half can be put outside of integration, and so and now as we see that this is the function that is integrated is actually equal to 1, we just need to subtract this one from this one, so lower limit from the upper limit. And what will we get here? So 1 minus modulus x minus modulus x minus 1. So if we simplify this expression, we will get 1 minus modulus x. So this is almost correct. Why I say almost? Because you see that actually all this is true. So limits of integration are these modulus x minus 1 and 1 minus modulus x only if x is from minus 1 to 1. As we see here, if x is, for example, equal to 2, if we are somewhere here, so our integral will be equal to 0. So as if we integrate our function, so joint PDF over y, and if we go along this line, so here joint PDF is equal to 0. So it is equal to this expression only for x's that are from minus 1 to 1. So the correct answer is that marginal PDF of x is equal to 1 minus modulus x if modulus x is less or equal than 1 and 0 otherwise. So we have got the marginal PDF of x. One may think, oh, it's just half of our big work, so now we need to find a marginal PDF of y. But let's have a look. We see here that actually our joint PDF is symmetrical. So if we change x by y and y by x, so nothing will change. So this figure is absolutely symmetrical. So if we change names of coordinate axes, so if this is y and this is x, nothing will change. So because of this symmetry, if we want to find marginal PDF of y, we'll do absolutely the same operations, just there would be x instead of y and y instead of x. And all the rest is the same. So we can say that marginal PDF of y is actually the same function. So 1 minus modulus y, if modulus y is less or equal than 1, and 0 otherwise. So after we have both marginal PDFs, we are to multiply them and to see so if the result of this multiplication is equal to the joint PDF or not. So if we multiply them, we will see that fx of x times fy of y is equal to 1 minus modulus x times 1 minus modulus y for when both, if both x and y are from minus 1 to 1 and 0 otherwise. So, and we see that this is not equal to their joint PDF. So joint PDF is constant inside this region, inside this square, and 0 outside of it. And multiplication product of marginal PDFs is not constant, and the region where it is not 0 is also not the same as here. So this region is just a square of this kind. So from minus 1 to 1, both for x and for y. So there is no equality. We see that joint PDF is not equal to the product of marginal PDFs, and so because of this we can say that x and y are not independent. So as joint PDF is not equal to the product of marginal PDFs, x and y are not independent. So what about covariance and correlation? As we found that x and y are not statistically independent, so they can be correlated or uncorrelated, we don't know yet. So let me rewrite formulas of marginal PDFs we have already got. So marginal PDF of x is equal to 1 minus modulus x for x is from minus 1 to 1 and to 0 otherwise. And marginal PDF of y so is equal to 1 minus modulus y for y from minus 1 to 1 and to 0 otherwise. To find covariance, we need expected values of x, of y, and of their product. So let's find the expected value of x. So according to the general definition of expected value of a continuous random variable, so it is equal to integral from minus infinity to plus infinity of x times PDF dx. So in our case, as the PDF of x is not 0 between minus 1 and 1, so this means integral from minus 1 to plus 1 of x times 1 minus modulus x dx. So, by the way, one may guess the value of the expected value of x even without these calculations, without applying the definition. How? Let us look at the graph of this function. Let us plot this function. Maybe I'll do this here. So the plot looks like this. So this function is 0 here and here and has shape of a triangle here between minus 1 and 1. So this is marginal PDF. So you see, this function is an even function. So it is symmetrical with respect to 0. And x is an odd function. And so when we multiply an odd function and an even one, the result of this multiplication is an odd function. And the limits of integration here are symmetrical. So they are minus 1 and plus 1. And maybe you know that an integral of an odd function with symmetrical limits of integration is equal to 0. So that is why we can say that the expected value here is equal to 0. So, or you can say that expected value is one of its physical meanings is the center of masses. Center of masses of this figure, of this triangle, and so, or center of symmetry, we can say. So if the PDF is symmetrical with respect to some point, this point is the expected value. So here, this PDF is symmetrical with respect to 0. That is why 0 is the expected value. But, so if you don't know all this stuff, so you can just calculate this integral. So to do this, you are to open these brackets. Then you are the first step is to split this integral into sum of two integrals. So you are to remove this modulus, and so for negative x's, modulus is equal to minus x, and for positive x's, it is equal to plus x. So you are to consider separately integrals from minus 1 to 0, so where x is negative, and from 0 to plus 1, where x is positive. And so you are to say that this integral is a sum of two integrals, one from minus 1 to 0, of x times 1 plus x dx, and the other one is from 0 to plus 1, so of x times 1 minus x dx. And so I don't want just to waste your time, but if you do so all necessary operations here, you'll get that it is equal to 0. So expected value of x is 0. And what about expected value of y? So it is also 0 because just they have the same PDFs. So x and y are identically distributed. They have identical PDFs, so identical distributions. So as e of x is 0, then e of y is also 0. Okay, so e of x is 0, e of y is 0. To find covariance, we need also e of xy, the expected value of the product of x and y. So what is the formula in continuous case? In continuous case, e of xy is in general, it is integral from minus infinity to plus infinity, a double integral of x times y times joint PDF. What do we usually do with double integrals? We reduce a double integral to an iterated one. So let's do this. We are to choose order of integration. So let the integral over x be the first one and integral over y be the second one. And so x times y, and as we are integrating over g, so, and inside this region our function is equal to 1/2, so x times y times 1/2 dy. As for the limits of integration here, they are just -1 and 1, so we are to take x's of the most left and most right points of our region, and they are -1 and 1 in this case, so from -1 to +1. And as for limits of this, of inner integral, so what we usually do, we pierce the region of interest with a line parallel to the axis, to the y-axis, as we are integrating over y. And so we need equations of these curves or lines. So where we enter the region of interest and where we leave the region of interest when we go along this line. And so we have already got them. So we already know these equations. We have found them previously. So limits of integration are modulus x minus 1 and 1 minus modulus x. And so what do we have next? We say that as we are integrating over y, then integral of y is y squared over 2. So we have integral from -1 to 1, and here we have x times 1/2 times y squared over 2 from modulus x minus 1 to 1 minus modulus x. And so as these limits differ only in sign and they are squared, when we substitute these limits here for y, so 1 minus modulus x squared and modulus x minus 1 squared are the same, and they're substituted one from the other, so the result is 0. So actually all this is equal to 0 as this expression is equal to 0. That is why all this is also 0. So our integral is 0. So what did we get here? So e of x is 0, e of y is 0, e of xy is 0. So that means that covariance is also 0. So as covariance of x and y is equal to e of xy minus e of x times e of y, and the covariance is 0. So these two variables are not independent, they are dependent, but they are uncorrelated because their covariance is 0. This is actually a rare case. Usually, if two variables are dependent, usually their covariance is also not 0, so usually they are correlated also. And so this is one of rare examples where we can see such a situation that x and y are dependent but uncorrelated.